Good Thursday afternoon, everyone. Welcome to lecture 16, Mathematics for Construction. If we look at our course outline here, we last lecture, we did a lot of vectors, and what we realized is that the topic of vectors really is an application of trigonometry, especially for you guys, right? So we did some problems here. There's a kind of bearing problem, right? These angles here, but they didn't say is bearings, but is the same concept, right? With a bearings question. We talk about resolving components, right? We could resolve vertical components and so on. We talk about how to solve some basic trigonometric equations like this here. Solving the same equation, sine x is equal to 0.85, negative 0.85, but depending on the domain, the answers is different, the working is different, right? In the course outline, we see here, we did APs already, do vector analysis. We'll talk about dimension analysis on next day. Oops, what is this? So we've pretty much finished LO4. We finished LO3 because that's calculus. We kind of do most of LO1, which is algebra and trigonometry. We do plenty algebraic techniques. That's what the first 10 lectures is for. We did all the trigonometry that you would need for a course like this. This is some statistics here. Statistics is the LO2. We'll talk about that from next week, right? We start talking about it today if we have time. We want to tackle this one here. Apply the use of matrices to solve problems, right? So the only way in this entire outline the word matrix shows up is this M1 here. That's a merit. If you don't get the merit, you could still pass the course. You just wouldn't be able to get a merit in the course, right? So matrices. What does the textbook say about matrices? Chapter 61. Right. So for your course, we see here, again, let me go back on top to the LO1. When you see matrices here, they say transposition, inversion. We're dealing with 2 by 2 matrices, right? How it applies to construction problems. And, you know, we have some real life scenarios, which you will see in your assignment, where you would have to use matrices to solve some problem in industry, right? But you really want to stick to 2 by 2. So when you're reading your textbook, don't really focus on 3 by 3 or anything greater, right? Stick to 2 by 2 matrices, right? And you'll see it as we go through, right? So the textbook has 2 chapters. Again, I give it to you all, matrices, right? 61 and 62. Now I said all sections, but you just want to stick to 2 by 2 matrices. So I'm gonna add that here, 2 by 2 matrices only, right? Even though I say all sections. So it's hard to say with sections because all the sections important, but they contextualize it for just 2 by 2 matrices, as we see here, right? The syllabus says up to 2 by 2. So all the sections are important, but some sections is only about 3 by 3 matrices. So just don't look at those. But the same thing you do for 3 by 3 matrices, you do for 2 by 2. So that's why you can't really ignore the section, right? I'll explain that more. So mainly use any solution a linear simultaneous equation. This is a linear simultaneous equation. First of all, it's a simultaneous equation because we have more than one unknown. We say there we need to find 2 things, x and y. We don't know what x is, we don't know what y is, but whatever values x and y have, they govern this equation here, they satisfy this equation, right? So it's a simultaneous equation because it's more than one equation, because it's more than one unknown. and it's linear. What is this linear thing really? Well, the powers are the unknowns is 1. So you see you have a x to the power 1 here, y to the power 1, x to the power 1, y to the power 1, right? All the powers of the unknowns are 1. That's why we call it linear. Now, you could do a graphical method to solve this one. Watch and see. Right? Let's see. I'll go on Desmos. We're going to cheat. We're going to cheat. We're going to do art. Right? This equation, x plus 2y equals 3. That's right. It's here. X plus 2y equals 3. So that's a straight line. That's what linear is, you know. Both equations represent a straight line. That's what I mean by linear. Linear, right? The next one, 4x minus 5y equals 6. 4x minus 5y equals 6. Ha! We cheat. Look at the answer here. Oh, it's some terrible looking answer. Wow. 2 point something and 0.4 something. Wow. That's not a nice solution, right? Well, ugly decimals there, but graphically is where the two lines intersect. So if one of these equations is not the equation of a straight line, then it's not a linear equation. It says non-linear, right? So this is where matrices have their use. Linear simultaneous equation. We have two equations, two unknowns. The highest power of the unknown in any equation is 1, so it's linear. We could represent this part here, the left-hand side, we could represent it as this matrix here. We'll get into that as we move along, right? Essentially, a matrix is a rectangular array of numbers, okay? Columns go vertically, right? So this matrix here has 3 columns. This is one column here, the first column. This is the second column here, the 2, the 4.8, 3. This is the third column here, 1, 7, 12, right? So the rows run horizontally. So this is our row here. Oops. And again, it. Okay. Rows run horizontally. Okay. So the number of rows in a matrix is usually specified by m. That's the first number. And number of columns by n. So it's a m by n matrix, right? So rows first, then columns. So this matrix here, what is this? A 2 by 3 or a 3 by 2? Well, how much rows does it have? It have 2 rows. Rows go vertical, horizontally, right? So I have 2 rows. So you start with 2. And then the next thing is the number column, 3. So I think that's self-explanatory, right? How you add, subtract, and multiply matrices? How you do that? Well, the matrices have to be the same size. That's the only caveat, right? Yeah, when I say size, I mean this here, 2 by 3. So you can add a 2 by 3 to a 3 by 2. It'll work so. 2 by 3 have to add to a 2 by 3. A 3 by 2 could add to a 3 by 2. The dimensions of two matrices have to be the same for you to add them or subtract them, right? Multiplication is a little bit tricky. We'll talk about that in a while, right? So say I add these two matrices here, 2, -1, -7, 4, and this -3, 0, 7, -4. You want to add them. Well, you just add corresponding elements. The 2 and the -3, that's this part here. The -1 and the 0, that's this part here. So corresponding elements, you add them. The location of an element is given by its row and column. So this -1 here is row 1, column 2. So row 1, column 2 in this matrix, first one, you add that to row 1, column 2 in the second matrix. That's why we might corresponding elements, right? This -7 is row 2, column 1. So row 2, column 1 and row 2, column 1. It's kind of easy for 2 by 2 matrices. Just add corresponding elements and you're good to go. Subtraction is addition, right? So to subtract 2 matrices, you're really adding them, you know, with the, you know, you add a negative numbers essentially. So it's the same thing, corresponding elements. You add them. Again, we really wouldn't get 3 by 3. We stick into 2 by 2 for this course. They want you to find a plus b minus c. So, I mean, these things not so bad, right? You just take your time and add and subtract corresponding elements. What's make it tricky is the negative signs, as usual. Let's make all our mathematics tricky at this stage. Where you have a negative sign, this give people problems. Multiplication by a scalar. What does that mean? A scalar is, as we finished last lecture, remember last lecture we talk about vectors. Vectors, a vector quantity is one which has both magnitude and direction. A scalar quantity has magnitude alone. So when they say scalar multiplication, they mean multiplying A, which is a matrix, by some number, not another matrix, right? So you see here, B is a matrix, B being multiplied by a number, C is a matrix, C being multiplied by a number. When you multiply a matrix by a number, you have to multiply every single element in it by that number. So if A is this, -3074, then 2A, you just double everything. This is going to be -6, which is here. This could be, well, 0 by 2 is 0, which is here. 2 by 7 is 14, which is here, and -4 by 2 is -8. So I think that's pretty straightforward. You just multiply every element in the matrix by the number. This is what we're doing here. 3b, this is 3 by this matrix here. So let's multiply everything by 3. And that's what these answers show you, right? Same thing for C. And then you just add up everything together because they wanted 2a minus 3b plus 4c. So you take two matrices at a time, you subtract these two, then you add these. The order not important, right? Matrix addition and subtraction is associative, right? And commutative. It don't matter the order you do it. Problems happen for people usually is when you're multiplying a matrix by another matrix. Matrices could only be multiplied by if they're conformable. What's conformable means? So we look at example here. A is a 2 by 2, B is a 2 by 2. First of all, you could only multiply it if the number of columns in the first matrix matches the number of rows in the second matrix. Okay? That's the only way you can multiply it in the first place. Actually multiplying it now is some trouble. As you see here, this is what gives people the trouble, right? How you multiply two matrices. So that's what we're going to talk about next. So, you know, we get some notes running here. Matrices, right? Plural is matrices, right? Singular is matrix. Just a rectangular array of numbers, number of rows, first number of columns. Row is horizontal, column is vertical. The dimensions is m by n, where m is the rows and n is the number of columns. So if you look at matrix A here, that is 2 rows by 3 columns. So this is a 2 by 3 matrix. A matrix B is a 3 by 2 matrix because that's 3 rows. You always list the rows first. Addition and subtraction. Okay, standard stuff as we saw here. Only matrices of the same size could be added. That's when I say dimensions. When I ask you for the dimensions of a matrix, that's what is given here, right? The dimension m by n. So to add and subtract matrices, the dimensions have to be the same. So I subtracting 2 matrices below here. Both of them are 3 by 2 matrices. So that's fine. Multiplying by a scalar is what we just saw. Oops. It's not so bad. Just multiply every single element by the scalar, right? So 3 by a matrix, so multiply everybody by 3. 2 by a matrix, and multiply everybody by -2. Standard stuff. The book doesn't do a good job of explaining multiplication, okay? They kind of say it here, but let me give you all some notes for that to more clearly understand what's really going on here, right? So, where is this thing? So let's take our time here, multiplying a matrix by another matrix. So a matrix can be multiplied by another matrix if both of them are conformable. What's this conformable thing? So matrix A on the left here is conformable to matrix B on the right if the number of columns in matrix A is equal to the number of rows in matrix B. So let's look at the dimensions, right? This matrix on the left here, this is 2 rows by 3 columns, so it's 2 by 3. Notice the 3 in bold. And this matrix here is a 3 by 2. 3 is in bold, right? So the number of columns in A, which is the 3, is equal to the number of rows in the second one, which is 3 as well. So if this number is the same, so is the inside numbers, as they say, write the dimensions down in the order you're getting matrices and look at the inside number. If the inside number is the same, these inside numbers, well, if they're the same, then you could multiply them. That's just figuring out if you could multiply two matrices, right? Actually multiplying is the next story by itself. We'll talk about that after. But when you figure out if you could multiply two matrices, what is the size or the dimensions of the result? Because if you multiply two matrices, you're going to get another matrix, right? The answer is to figure out the dimensions of the result, you look at the outside numbers. So you see this 2 here, this is number of rows in the answer, and this 2 here is the number of columns in the answer. So the answer will be about 2 by 2 matrix. That's how you know. So again, when you write the numbers above, the inside numbers are equal, therefore the matrices could be multiplied. The dimensions of the answer is given by the outside numbers in the order you see there. So 2 by 2. Matrix multiplication is not commutative in general. What's commutative? Remember numbers? 3 by 5 is 5 by 3. The order don't matter, right? Multiplication of numbers is commutative because the order don't matter. That's not the case with matrices. Matrices actually, in general, if you have two matrices, A and B, A by B is not B by A in general, okay? So how do you multiply the matrices now? So they give you an idea here. It's a kind of complicated algorithm, right? If you look at what they're saying here, let A by B be C, C1, 1, C2, 2. First of all, how do I know the answer is a 2 by 2? Well, everything is 2 by 2. So the answer is going to be a 2 by 2. All the numbers are 2 by 2, and 2 by 2. So these inner 2's are the same. So it could be multiplied, and the outer 2's tell you the dimension of the result. So the answer is going to be a 2 by 2 matrix. But you see the C11, and the answer, that C11, that is really the first row in the first matrix multiplied by the first column in the second matrix, right? How you multiply rows by columns. So you might have to see that live. You might have to see that live, right? So let's look at the actual matrix multiplication algorithm. So let's do a question, right? So let me put these matrices here, right? 2, 3, 1, -4. So let me see. 2, 3, 1 minus 4. So I have 2, I have 3, minus 4. And next one is minus 5, 7, minus 3, 4. So we want to multiply these two matrices here. So they go through a whole bunch of stuff here for that, right? And they have an answer. Let's see how to do it. So you're gonna get an answer. You're gonna get a 2 by 2 answer. So what they did is they represented the answer as unknown variable with subscripts. Okay, so, and you don't need to use the letter C, okay? You really need, they just use that here because the first two was A and B, right? So how do you get the first C11? How do you get that? Well, C11, that means C subscript 11. That means the first row, first column in the answer. This element here is located in the answer in the first row and first column. So we need to multiply the first row in the first matrix by the first column in the second matrix. So that will be 2 by negative 5 and plus 3 by negative 3. That's essentially what they're saying here. So let me duplicate that, right? So this answer here, this is two things being added. Okay, so two things being added here. What are the two things? 2 by negative 5 and 3 by negative 3. 2 by negative 5, 3 negative 3. Okay, so that was first row, first column. The first row here multiplied by the first column here. What is C12? C12 is located on the first row, second column. So I multiply the first row by the second column, right? So that's 2 by 7 plus 3 by 4. So again, it's two things being added. 2 by 7 plus 3 by 4. You always add them. All right. This C21, what does this mean? This element is located on the second row, but first column. So you have to multiply the second row here by the first column. So 1 by minus 5 minus 4 by minus 3. And what is giving people trouble is that minus sign. Right? Sometimes they just forget it. So again, C21 is really adding two things. Which two things? Second row, we multiply by first column. So 1 by negative 5. Right? 1 by negative 5 minus 4 by minus 3. Okay? Minus 4 minus 3. And the last one, C22. Second row, second column. Again, you're adding two things. Which two things? Yeah. Why is two things? Is because it's two elements in a row and two elements in a column. That's why I added two things. So C subscript 2 is the second row by the second column. So second row by second column. 1 by 7. Write that. 1, 7 plus negative 4 by 4. Right? I know it looks ugly, I know it looks long, but that's really what's happening here. As I multiply matrices, you look at an individual element, look at the location of the element. Whatever row that element is in, that is the row in the first matrix you're going to use in the multiplication. And whatever column that element is in, that is the column in the second matrix you're going to use. So for example, C21 is the second row, first column it's located. So we need to multiply the second row by the first column. So 1 by the negative 5 and the negative 4 by the negative 3. And I hope this makes sense now. It's really just to simplify. So let's take our time. What is this here? This is negative 10. 3 by minus 3 is minus 9. 2 sevens are 14. 3 fours are 12. This is negative 5. Negative 4 by negative 3 has plus 12. Let's try 12 there. This is 7. And this is negative 16. Right? I can simplify again. Minus 10 minus 9 is minus 19. 4 and 12 is 26. Minus 5 plus 12 is the same as 12 minus 5, 7. And minus 7 plus, sorry, 7 minus 16, that should be negative 9. Okay? What answer they got here? Negative 19, 26, 7 minus 9. Yeah, that's the answer they got up here. Right? And that's how you do it. You just have to take your time. They did it in pieces, each piece. You see the C1 one that did the 4 pieces together, right? But you don't need to do it like that. You could do it in place. It just looks a little bit messier. There's a lot of horizontal space you have on your paper to really represent the individual sums, right? But it's doable like that. I don't advocate doing this. You'll get lost. All right, do it in place like this here. You could actually see everything happening. And then it's easy to check over your work. All right. Now, what we're gonna do, what I want you to do now, right? This is what I want you to do. Let me duplicate this, put this down here. You could call this example. We'll give them different names, right? So this is example 1 here. Example 1. Now, this is what I want to do here, just to show you and give you some practice. How about we reverse this? How about we say, I want, just to give you all some practice, right? So up here, I had the 2, 3, 1, 4 matrix multiplied by the 5, 7, 3, 4. What if I reswap them left to right and I get this here? What will be the answer when I multiply these two matrices together here? Will it be the same as this? What I'm showing you here is, let's check to see if multiplication of matrices is commutative. Commutative means the order doesn't matter. A by B is B by A. We know multiplication of numbers is commutative. 3 by 5 is 5 by 3. But is it the same with matrices? So I reverse the matrices here, and I want you to do this for me now. Use the same idea that I showed you there and find the answer, and look at the answer and see if it is what we got before, okay? So we're gonna take the same approach as up here. Just duplicate this. Drag it down here. Just take out this part. So, okay, let me just neaten this up here now. People get us wrong because they just don't take the time. So reset everything. Okay. Each element is the sum of two things. So this first element, this top left, is row 1, column 1. So 5, 7 by 2, 1. Right? So negative 5 times 2 plus 7 by 1. The top right is row 1, column 2. So row 1 by column 2. So negative 5 by 3 and 7 by negative 4. Bottom left is row 2, column 1. So row 2 by column 1. So negative 3 by 2. And 4 by 1. And last one, bottom right, is row 2, column 2. So row 2 by column 2. So negative 3 by 3. And 4 by negative 4. So there you go. Let's check over your work, negative 5 by 2 plus 7 by 1, negative 5 by 3 plus 7 by negative 4, negative 3 by 2 plus 4 by 1, negative 3 by 3 plus 4 by negative 4. Right. I could duplicate this now and just simplify this. So this is negative 10. This is 7. This is negative 15. This is negative 28. This is negative 6. This is just 4. It's negative 9. Negative 60. Negative 10 plus 7. That's negative 3. Negative 15 minus 28. That is 43. Negative 43. right? Minus x plus 4, minus 2, negative 9, negative 60, negative 25. And that's, I think that should be the answer there. Now, it's immediately obvious that multiplication of matrices is not commutative, because when I reverse the matrices, I didn't get back the same answer. I got a completely different answer, right? So always keep this in mind. Matrix multiplication is not commutative in general. In general, it's sometimes you will be given two matrices, and it don't matter how you multiply them, you just get the same answer. We'll see that later on. But that's not the norm. Okay, that's not the norm. So I hope everybody understood this. To give you all an example now, another one to do. Now look at this question here. Look at this question. Could these two matrices be multiplied? And if they could be multiplied, what does the answer look like? What is the dimension of the answer, right? And then actually do the multiplication. So there's a little trickier one here now. These two matrices have different dimensions. So you might think to yourself, well, you know, I can't really multiply them. But these were the two matrices up here. You see, this, pull this down here. This is a 2 by 3 matrix, and this is a 3 by 2 matrix. The inner numbers are the same, so these matrices can be multiplied. And what is the dimension of the answer? Well, that's what the outer numbers say. The outer numbers say the answer is a 2 by 2 matrix. So I know here the answer is a 2 by 2 matrix. So I'll come here now and write something like that. Okay. I know the answer is going to be a 2 by 2 matrix. It's just to figure out what it is. So again, you know, you could label your answer. Again, you know, we could call it, well, this is C11, C12, C21, C22. How you know what to multiply to get each of these elements here? So if you look at C subscript 1, 1, the first element, top left, right? That's the first row, that's located in the first row, first column. So I need to take the first row of this matrix and multiply it by the first column of this matrix. Now this has 3 elements being multiplied by 3 elements. So the 3 will go with the 1, the 2 will go with the 5, negative 5 will go with the 3. So it's 3 sets of additions here for this element. That's because our row have 3 elements, which is the same as the column, which has 3 elements. So it's 3 additions. So therefore, this element here, if let's try and do this here now. This first element is really 3 things being added. Okay? And all the elements will be 3 things being added. Why? Because they're conformable. Conformable means the number of columns in the first matrix is the number of rows in the second matrix. So these columns here is 3 things, and this row here is 3 things. So it's 3 things being added. Here it was 2. right? 2 rows, wait, 2 columns here by 2 rows, right? So that's why I have 2 things being added. Here now you have 3 things being added for each element. The hint is the number of things to add is determined by this inside number here. You see the inside number 3? That tells you how much things you need to add. So the inside number is 3, so I have 3 things to add. So what to do? Finish this out. Take your time and multiply this out and tell me what answer you get. And then for practice, we could try other questions, right? But do this one first. This is example 3. Tell me what you get. Okay, so as I said before, the inner number 3 tells you how much things you have to add when you multiply a particular row by a particular column. So there's 3 things we'll have to add up. So let me just copy this here for each of these guys, right? And then we just need to figure out inside each of these brackets here, we need to multiply 2 numbers. So first row, first column is the 325 by the 153. Right? Let me put this up here so you get more real estate. -3 times 1, 2 by -5. And -5 by 3. Right, so that's first row, first column, right? -3, 2, -5, -3, 2, -5, and 1, -5, 3, 1, -5, 3. First row, second column. So first row, second column. So we could actually copy this and just change the second number. Second number will be this will be -4. This will be 2. And this will be -6. Right. So -3 by -4, 2 by 2, -5 by -6. This lower left corner here is second row, first column. So the first numbers will change now. This will be 1, this will be -6, this will be 4, right? 1 by 1, -6 by -5, 4 by 3. Then bottom right is second row, second column, second row, second column. So the -4, the 2, and the -6 would stay, but it's 1, -6, and 4 for the first numbers. So 1, -6, and 4. 1 by -4, -6 by 2, 4 by -6. So at this point is where you really should be checking over your work, making sure the pairs and numbers make sense. And then, you proceed to simplify, right? So to duplicate this, simplify these things here. -3 times 1 does -3, 2 by -5, -10. This is -15, right? +12, +4, +30. This is 1, positive 30, 12. It's negative 4, negative 12, negative 24. Right, now we keep going. All these numbers are negative. So this is 25, 26, 27, 28. So this looks like negative 28. This number is positive, looking like 46. Right, that top right corner number there is looking like 46 when you add these numbers here. This bottom left number looking like 43. And all these numbers are negative here. It's probably negative 40. Make sure. I think that's it there, right? So, you know, like it's really addition and subtraction and multiplication, you know. It's really arithmetic, right? The actual core mechanics of it is primary school maths, right? A 9 or 8-year-old could do this, but the order of the rows and columns is the tricky part. What row by which column? I just had to pay attention to negative signs, right? That's it really tricking it. I think there's the final answer here. Some people still manage to not get it, you know. Some people came close, but that's it there, right? Hope you all understand that. So it's just to really practice that, and I'll give, you could do the problems in the textbook. Like you see here, wow. This is easy. This is just asking you to add things, right? The multiplication ones, I mean, you could try this, but these kind of ugly because it's fractions, right? And they give you the answers here. So you could try the questions in the textbook. Now, even though the textbook talks about unit matrix, the examples they give for things like determinants and the inverse and these things, I find the examples they give a little bit out of the way, because you all would know what these things are. Right? These are phasors or complex numbers, okay? Something not on your course. So when you're reading this, you'll be like, what it is them doing here? Kind of confusing, right? Because I mean, it is chapter 61 towards the end of the book. So they're assuming you know all this stuff from the beginning parts of the book, right? But these things not on your syllabus for this course. So that's why I'm going to give you some extra notes. We're going to talk about all these things: the inverse, the reciprocal, the determinant, the identity matrix, what singular matrices are. We're going to stick to 2 by 2, and then we're going to show how to solve simultaneous equations, right? So let me forget about the book for now, because the book kind of confusing, right? Where's this identity matrix that they talk about? Let's see. The identity matrix. So given an m by n matrix, okay, somebody give you a matrix m by n, the identity matrix is a n by n matrix, or we call a square matrix. A square matrix has the same number of rows and columns. I think that makes sense. That's self-explanatory, right? But the identity matrix for a particular matrix, you're looking at the columns, this n, the second number in the dimension, right? That number of columns, a square matrix with ones on the diagonal. That's what the identity matrix is. So if I give you this matrix here, 2, 5, right? This is a 2 by 3 matrix. Since it has 3 columns, right? The identity matrix is a 3 by 3 matrix of zeros, except for the diagonal, which is just ones. We call this the diagonal, going from left to right, the middle elements, right? The nice thing about the identity matrix is any matrix multiplied by identity matrix is itself, right? So for this matrix here, its identity matrix is a 3 by 3 matrix. When you multiply it, you get the original matrix, okay? Of course, you know, you can't change the order of this because this is a 2 by 3. If you put this identity matrix in front of this here, it wouldn't work out. You can't multiply a 3 by 3 matrix by a 2 by 3. It's not conformable. But the other way around, like this here, is fine. So that's really what the identity matrix is. Think of the identity matrix as like the number 1 for numbers. You know, like 1 is the identity for multiplication. Any number by 1 is itself, right? So 5 by 1 is 5. Think of it like that. So 1 is the identity for multiplication. For numbers, the identity for matrices is this identity matrix here. It's a bunch of zeros, mostly zeros, but just the diagonal from top left to bottom right is 1s. We have another concept here. We stick into 2 by 2, right? So, you know, we want to talk about the determinant of a 2 by 2 matrix. So if somebody give you a 2 by 2 matrix, A, B, C, D, right? Again, we letter it from, we do it from row to column, right? So we fill out the first row, A, B, and then you fill out the second row, C, D, right? That's how we specify a general matrix. The determinant is a number, and the number is this product AD minus this product BC. So it's a difference of products, it's a number. So the determinant of a matrix is a number. But for a 2 by 2 matrix, it's possible to give a formula. For the other matrices, the formula looks kind of complicated. It's very easy for 2 by 2 matrices, right? So that's the determinant there. Now, we want to talk about the inverse. So given a 2 by 2 matrix, ABCD is 1 over the determinant multiplied by this rearranged matrix here. So if you look in the textbook, they talk about this, right? They say for any matrix, they use PQRS. Oh gosh, I use an ABCD. What are you going to do about it? They say interchange P and S. The top left and the bottom right, interchange them, switch them. So you get DA, right? And then change the signs of the top right and the bottom left. So you see B comes minus B, C becomes minus C. And then divide by the determinant, or multiply by 1 or the reciprocal of the determinant, right? That's what the inverse is. The nice thing about the inverse, if you multiply a matrix by inverse, you get the identity matrix. And this could be used to solve equations, matrix type equations, right? A singular matrix is a matrix with a determinant of 0. So a singular matrix does not have an inverse. So, I mean, probably make this a little bit more obvious, right? Singular matrices are matrices where the determinant, which is this value here, is 0. Obviously, if the determinant is 0, 1 over 0 is not a number, it's indeterminate, so that wouldn't have an inverse. So just be mindful of this here. Let's put it in a nice color, right? So if we multiply a matrix by its inverse, we get the identity matrix. So let's try that. Let's try that. Let's take a matrix ABCD and multiply by the inverse. This is the inverse here. The inverse, see it here. So we're multiplying by the inverse. Now this is a scalar. So we could take this and put it to the far left. And then we could multiply the matrices like normal, okay? What is this? Right? If we multiply the matrices, forget this determinant here, that's just a number. So we could say that the answer is something like this, right? So it's a 2 by 2. So we multiply 2 by 2 by 2 by 2, the answer is going to be a 2 by 2, right? So we know that this is the case here. These two matrices here, when I multiply them, I'll get a 2 by 2 matrix. This number here is on the outside, okay? I want you all to do this for me now. Multiply these two matrices here, the letters, and tell me what you will end up with. Okay, simplify this stuff in brackets here. We don't have numbers now, we have letters. So write the expressions in alphabetical order. Okay, so like if you multiply A by D, don't write DA, write AD, right? If you multiply C by B, don't write CB, say BC. Always write each expression in alphabetical order. So multiply them. Oh, these two matrices here. And tell me what you get here. Obviously, you're not going to get a single number. You're going to get expressions. This is to practice your algebra, okay? So we, top left, first row, first column. So AD minus BC. That's what you'll get here. Let's scroll. AD. Actually, I could just write the expression, right? AD minus BC. And as I write it in alphabetical order, right? Top right, first row, second column. This is minus AB plus AB. Minus AB plus AB. Bottom left, CD minus CD. Okay. CD minus CD. And bottom right, bottom row by right column, minus BC plus AD. Minus BC plus AD. So, yeah, you know, you get an answer like that, right? But you should try and simplify it, right? What is this minus AB plus AB? This is 0, yeah. This is 0. And this CD minus CD here, this is 0 too. And this AD minus BC, that's what this is here, AD minus BC. Just rearranges AD minus BC, right? And if you multiply by a scale of 1 over AD minus BC, then these things will cancel it. So essentially, what do we get? This is 1, this is 0, this is 1, this is 0. When you multiply a matrix by its inverse, you get the identity matrix. And that's really cool because it means you could remove a matrix from an equation by just multiplying by its inverse. So if we have a matrix equation, multiplying by the inverse on both sides kind of undoes that matrix on the particular side that you have it, right? So just a new note here. Singular matrix is one has a determinant of 0. And we could grab this, stick that down there. Probably change this. Singular matrix doesn't have an inverse, right? Now let's use that technique that we just saw, this one of the inverse, to solve simultaneous equations, right? How do I represent this in matrix form? Could I multiply two matrices and get a matrix as well? Turns out you could do that. The matrix form of this algebra here is this. Look at this. If you multiply this 3 minus 2, 4, 3 matrix by this column matrix xy, you'll get what? 3x minus 2y, right? And is equal to 7. So the left-hand side, when you multiply it, you get what we call a column matrix, right? Similarly, this is a 2 by 1 matrix. This is a 2 by 2. If you see the two inside numbers are the same and the outer two numbers are a 2 by 1. So the answer will be a 2 by 1. So 7 is equal to the first row by that is only column, 3x minus 2y. But as we're given here, 3x minus 2y is 7. Similarly, second row by the only column is 4x minus 3y. But that's equal to 10. That second element in the column matrix is equal to 10, but that's what we have here. So it's very easy to take a pair of simultaneous equations and convert it into a matrix equation. So how you would solve this equation here? Well, you should probably find the inverse of this matrix, right? So we could find the determinant. That's the determinant there. AD minus BC. So minus 3 by minus, well, 3 by minus 3 minus 4 by negative 2. Minus 9 plus 8. So this is determinant here. So what we want to do is we want to multiply both sides of that equation by the inverse. So this equation here, 3 minus 2, 4, 3x, we want to put the inverse on the left. And if you put the inverse on the left, you're going to have to put the inverse on the left of the 7 and 10. That's what we do here. Remember, the inverse is 1 over the determinant by the rearranged matrix. So the original matrix, we swap A and D, and we put minus signs for B and C. So 4 become negative 4, minus 2 become 2. And this 3 and negative 3 get swapped. Now it's really just simplify things, right? This negative 1 over 1, we could multiply everything here by negative 1 and everything here by negative 1. This is the answer we would get, right? Change all the signs of these things here to negative. Change all the signs of these things here to negative. Now, if we multiply these two matrices now, we just change the brackets, right? So notice I put brackets around these two matrices here first. So instead of multiplying this middle by the right, I multiply these two. What will you get? When you multiply these two matrices here, what will you get? You could duplicate this and change it up. So a 2 by 2 by a 2 by 2 is another 2 by 2, right? So we'll just have a single 2 by 2 matrix here. And with the usual thing, each element is the sum of 2 multiplications, right? do this for me now. If I multiply these two matrices here in the square brackets, what will I get here? And then these two matrices here, this is a 2 by 2 by a 2 by 1. So the number of columns in this, which is the number of rows in this, is 2. So they're conformable. And the answer is a 2 by 1 matrix. So we know here we're going to get a 2 by 1 matrix. So again, two things are going to get here. So these two matrices here, I could take out the brackets, right? And you could multiply them. Multiply these two matrices here, you'll get a 2 by 1 matrix. And multiply these two matrices here, you'll get a 2 by 2 matrix. Take your time and do that. So we trying to multiply these things here. Top left element is first row by first column. So 3 3s minus 2 by 4. So this here, 3 by 3 minus 2 by 4. Right? Top right is the first row by second column. So 3 by minus 2 plus minus 2 by minus 3. Bottom left is second row by first column. So 4 by 3 plus negative 3 by 4. And bottom right is second row by second column, 4 by negative 2. Negative 3 by negative 3. Right hand side now, the top element is the first row, first column. So the first row by this column here. So it's 3 by 7 by minus 2 by 10. Then the bottom one, the second row by the only column, 4 by 7 minus 3 by 10. So we simplify this here. This is 9. This is 8. Negative 6. 6. It's 12. Minus 12. It's negative 8. This is 9. This is 21. Minus 20. So it's 28. Minus 30. So again, let's go in and simplify. 9 minus 8 as 1. Minus 6 plus 6 is 0. 12 minus 12, 0. Minus 8 plus 9. That's 9 minus 8. So as 1. So you don't even need these brackets again, because you get one matrix. And on the right-hand side here, 21 minus 20 is 1. And 28 minus 30, -2. Now this is the identity matrix, right? A 2 by 2 identity matrix. And a 2 by 2 identity matrix by a 2 by 1 column matrix is the same thing. It's the same matrix. So it comes as though I don't really have this here. I could take that out. And then if two matrices are the same, then the corresponding elements are the same. So x is 1 and y is -2. Look how easy it was to solve a simultaneous equation. Linear simultaneous equation using a 2 by 2 matrix. The algebra is not very sophisticated. Like if you had to change the subject of the formula to substitute one equation and an x equation, like if you're using substitution method. Or if you had to multiply the equations and then add them or subtract them, as the case may be, if it's method of elimination, right? You get away from all of that if you know matrices, right? And this is the power matrices have in the real world. In the real world, computer software that solves equations and so on. Software packages that do mathematics, they use matrices, right? A famous example is MATLAB or Octave, right? If you could go online, you could see MATLAB. Very expensive software used by engineers, right? It has its own programming language, but MATLAB is short for Matrix Laboratory, right? So it's computer packages where you write software to solve problems in engineering. Okay, so you say use it in robotics, signal processing, mechanical engineers and civil engineers use this a lot for advanced computer aided design, right? A free version, a free alternative to MATLAB is Octave, right? Where you represent matrices. See here, they have a matrix 4, 9, 2, and A is a matrix, and you divide, solve the system equations, right? And you can plot graphs and curves, and is like way better than Excel, way better than Excel, but you have to learn a little bit more, right? It's way more powerful. But these things use matrices, see, vectors and matrices. That's what computational mathematics is about, using vectors and matrices. So all this stuff we learn in here, it is used in the real world. Just you mightn't use it, right? This is how you take a simultaneous equation. Make sure it's the same format, xy, xy, right? Because you're multiplying by a column vector here, xy. But the level of mathematics here is not sophisticated. It's basically subtraction, addition, and multiplication. And you get your answer. I hope this makes sense. So what does the textbook say? Textbook gives you some examples of finding the inverse. You say 1 over the determinant multiplied by the shifted elements. They give you some exercises here with the inverse items. But don't read this. Determinant of a 3 by 3 matrix. This is real work, okay? This is not going to be tested for you guys. So just bypass the 61.6 completely. Anytime you see 3 by 3 matrix, don't even bother. And you see here the inverse of a 3 by 3 matrix, don't even look at this. This is not on the course. We're not doing that. End of chapter. Solution of simultaneous equation by matrices. Stick to 2 by 2. Right? 2 by 2 matrices, we use it. And they give you a nice algorithm here. Represent it in this format, find the inverse, multiply by the inverse, solve by, then doing the actual matrix multiplications, right? We just need to practice this. So I'm going to give you all a question. And again, When you see a 3 by 3 matrix, don't even look at that. Don't even look at that. That's not any cost, right? With the adjoint and the matrix are cofactors. And this here, bypass this to 62.2. We're not doing this. Ignore all of this. This is not part of your course. So it's just a little bit of each chapter you need to know. All this here we bypass it. So when you see an equation with 3 unknowns, x, y, and z, that's not for you. We're just doing 2 unknowns, like something like this here. Okay. So I'll just give you all an example that you could work out now. What would I call this boy? This is example 3. I would have called that problem 1. So just show you the technique. Problem 1. So I'm just proceed this up to make it look a little more presentable. So solve using a matrix inverse method, meaning use matrices and find the inverse. First, you write the equation in matrix form. You don't need this stuff here, right? This matrix on the left, the 2 by 2 matrix on the left, we want to find the inverse. So the inverse is 1 over the determinant by the shifted matrix. So you see 1 over the determinant by the shifted matrix here, we shift around the elements. And then we just multiply both sides by that. That's what the square bracket show you. And it's just to do the multiplication. You will get identity here. That's what removes the matrix. Okay. You see this matrix was on the left here. How do you remove it? One way of removing it is just to multiply by its inverse. When we multiply by the inverse, we will get the identity. And then the identity by xy is xy. So you see how you remove the matrix, right? So removing a square matrix is easy. Just multiply by the determinant. And we just stick into 2 by 2 matrices. Right? So this was problem 1. I could give you a new problem here, problem 2. And I could write the equation deliberately in an incorrect, well, not incorrect, in an inconvenient way. So I could say 3y plus 5x equals something, right? And down here for, okay, I should say plus something equals 0. 4y minus 3x plus something equals 0. Let me sit down and make up a question here. Make this negative. So that's the problem there. So I give you two equations, 3y minus 5x plus 9 equals 0, and 4y minus 3x minus 1 equals 0. Solve this using the matrix inverse method. I think this is supposed to be -9. -9 equals 0, right? So it's -9 there. Just small typo.